In this video, we will have another electric potential calculation. This is finding the electric potential of a finite line charged particle. In our previous video, we derived the relation of the electric potential for an a ring charge. Okay. Now, in this part 3, we will focus on the calculation of the finite line charge particle. Now let us recall that if we have point charge, okay, this is a point charge whose charge is positive and this is spread all over the surface of the sphere. Now at a point P from the center, let us say R, we can always calculate the electric potential at that point. And to answer this is, we found out that the electric potential at point P whose distance is R with a charge Q is 1 over 4 pi permittivity. This is our electric constant divided by the distance. So it is very simple to calculate because we know the electric potential of a point charge. But the question is this formula again applicable to another continuous charge? This is not a point charge. This is continuous, okay, because this is kind of line, and we have this charge distance of the line charge because this is finite. This is a finite, which means that the length was identified by, in this case, our length is 2a because from 0 to positive a and 0 to negative a. So the length of the line is, and line conductor is 2a. Now, if we have this point and we are asked how much is the electric potential at the distance x from the perpendicular distance from the center of that line, what is the electric potential? The question is, can we use this formula again? The answer is no. Why? Again, this is not a point charge. This is a line charge. So therefore, we cannot provide, you cannot use this formula. So the question is how? How? Again, we will consider an infinitesimal, a segment of this line, a very, very small line, whose charge is dq and whose length is dy. Okay? This should be dy, means it is a very, very small y, because we will assign this as, now the center, from the center of that point charge, this is already a point charge because this is infinitesimal charge. So therefore, we have this distance r. Okay? So in this case, we can use the principle of point charge. Meaning, if I multiply the electric constant by this infinitesimal charge, take note that the whole charge is q. Okay? So this part is dq. So therefore, if we multiply the constant by this infinitesimal charge dq over this r is the distance from the center of that point charge dq to p. So the result is infinitesimal electric potential. Infinitesimal because we are using an infinitesimal charge. But if we integrate this both sides, we will come up with the electric potential at that point as a whole charge q. Okay, so integrating both sides, then this will be the result v, which is the electric potential at that point, the electric constant, then the integral of dq over r. So in other words, if we can evaluate this integral, the result is the electric field or electric potential at that point. So the question now is, what is dq? Okay, what is dq? Now take note that dq is located above 0 in this case. So from 0, this is 0 y, above is positive y, then below is negative y. But the positive y is only up to a distance of a, while the negative y is up to a negative of a. So therefore, this charge segment will move towards the y-axis. It can be positive above and negative below, 0 at the origin. So what is dq? Okay, Now take note that the infinitesimal charge has a length of a very, very small length of y. Call this as dy. So therefore, dq can be now expressed in terms of the linear charge density because this is a line. So therefore, the linear charge density lambda, which has a unit of coulomb per meter, so meaning again, lambda is the charge per length. For every meter of this, we have the value of the charge. So we need this one. Why? Because we cut a segment of this line. Now what is, how to compute the linear charge density? The answer is, because the total charge is Q. This total charge is Q. So therefore, Q divided by the length. Okay? But the length is what? The length of this wire is twice A. So therefore, it should be Q over 2A. 2A means the length of the wire from this point going to this point. So this is 2A. Then the total charge is Q. So dividing that value, the result is the linear charge density. So therefore, for an infinitesimal charge, okay, the linear charge of this is still the same. It should be charged because this should be Q over 2A because this should be the charge length. This is charge coulomb per and this meter. So therefore, another way to calculate the linear charge density is considering this small charge, and the small charge has dq and the length is dy. So therefore, this result must be the same because this is per length. Okay, for every segment we have only one value of that, and that's the linear charge density. So therefore, we can take the diagonal product of this, take the diagonal product, solve for dq, then we have the linear charge density times dy. This is the value of q. This is to be substituted here. Now r is what? Take note, this is a right triangle, okay? Because this is 90 degrees. So therefore, we can solve for r in terms of x and y, and that is the square root of x squared plus y squared using the Pythagorean theorem. Because this is a right triangle. So substitute here and substitute the infinitesimal charge or dq here. So we come up with this result. We have the 1 over 4 pi permittivity integral from negative A because this is from A, negative A going to, we will let the infinitesimal charge moving from, it starts from negative A and we end up with positive A. So then dq again is, okay, this is the dq and this is r. Now take note that if we evaluate the integral, this one is constant. Okay, so this can be placed outside in the integral, but this term or this divisor, which is our r, cannot be placed outside, unlike before. Why? Because take note, r is keep on changing. When this charge moves from negative to positive A, this r will keep on changing. Take note that it is r is maximum at the extreme point, the starting and the final point, but the smallest r is at the origin. So therefore, this cannot be placed at sun because this is variable. It varies with, and this x squared also will be affected because it is within the square root size. So therefore, we will move the linear charge density. Okay. So the question now is how to evaluate this one. Now take note, when you look at the integral, we cannot apply our basic integration here. Why? Because this is second degree. Okay, and we have no y here. If we have y in this one, then we can apply the substitution method. Okay, basic substitution. Now, therefore, we will evaluate the integral by, okay. By the way, we can replace, because we don't know what is linear charge density yet, so we can replace that with, let's return the value of q over 2a. This should be the value of the linear charge density. So then, okay, so we will now to evaluate the integral. Now, all you need to do again is to, in order to evaluate this, because if this factor can be evaluated after evaluating this one, we have to multiply this, the entire constants here. Then the result is the electric potential. So the technique, the strategy is we will use the trigonometric substitution. We will involve right triangle. Why? Because this is a kind of uh, because we have x squared and y squared, so therefore we can form right triangle. So if we consider this triangle, a right triangle whose angle theta, okay, and this is x and y, we can say that this hypotenuse is what? Square root of x squared plus y squared. So therefore, look at this one. So this is a kind of strategy. If it involves square, then think of the square root. No, we have x squared plus x squared, so we can think of the Pythagorean principle. So in the Pythagorean principle, we can use the Pythagorean theorem. Or take note that we have the identities that involves right triangle. So we call it a Pythagorean identity. So therefore, it's good to start with this strategy. This is a strategy. This is a trial and error method. Because the purpose of the method, substitution method, means we will replace the complexity. Because this is complex. No? This is not basic because we cannot apply. If we cannot apply the basic rule of integration, then it's treated to be complex. So, meaning it's composite. So, therefore, we have to do something about it. We will substitute it here. Okay? And we will try that to substitute in such that from complexity, it will return into simplicity. So, simplicity means we can apply the basic rule of integration. So, this is again a strategy. Okay. So, to do it is okay. Now, if we take tangent of this, if I divide x over y over x, what is the meaning? Y is the opposite of theta and x is the adjacent. So, dividing opposite of adjacent is tangent. So, therefore, the tangent of theta is x over y. Take the diagonal product of that y because we want y value. We will replace y here. So, therefore, we can now substitute y with x tan theta. We involve theta as a dummy variable in order to, again to make it simple to integrate. Okay. Now, remember we need dy. We will replace dy. So therefore, this is a kind of technique that we will replace the y's with thetas. We will replace y involving theta. So, for example, y was converted to x tan theta. So therefore, we involve theta. X, nothing to worry. It is a constant. It won't change. Okay, the x. So therefore, again, we need dy. So where can we see dy? You can take the derivative of that. Take derivative of dy with respect to theta. So therefore, dy over theta, the integral of x is, this is coefficient, so copy it. Then the tangent, derivative of tangent is secant squared. So therefore, we can now solve for dy by diagonal product. So dy is x secant squared theta d theta. Okay, we are now ready. This will be substituted here. Okay, then this y value should be placed here. Okay, let's proceed. Okay, so the 1 over 4 pi primitivity copy q over 2a, the integral from negative a to a, and okay, your dy now becomes x secant square theta d theta. This one. This is it. Now x square root x squared, the same, plus instead of y, take note ratio 2. We will replace y with x tan theta. Okay, we are now on the way to simplify this. So take note, this is square. So therefore, extract the square. So nothing changed here except this one. Except this one. This will become x squared, log exponent, x squared tangent squared theta. Okay. Now notice that we have two terms under the radical. And we have the common x squared. So we can take out the common. Okay. Leaving what? So x squared as a common, then 1. Because this is x squared plus, remove the x squared, leaving tangent squared theta. Okay. Now, look at this one. What is tangent squared theta? Okay. So, we'll place it for writing space. See. What is tangent squared theta? What is tangent squared theta? Take note, this is 1 plus tangent square is under the Pythagorean identity. So you have to recall your Pythagorean identity. Now remember, in your Pythagorean identity, the 1 plus tangent square theta is what? Secant squared. So meaning, we can replace with this with secant squared. So, here it is. This is now secant squared. This is the equivalent of 1 plus tangent square theta. Okay, take square root of that. We have two pieces of x and we have two pieces of secant theta. So take note square root. Okay, and these are forming product. So therefore, the square root of x squared is x and the square root of secant squared theta is secant theta. Okay, this is it. Okay, so this is the square root of x squared and this is the square root of secant squared. Okay, notice above. X can be cancelled out. Okay, then this is two pieces of secant and this is secant, so we can cancel one, so leaving secant only. So this is the result. Now, look at the result. We still on the process to integrate. Why? Because we use the trigonometric substitution. Okay. Now the purpose of the trigonometric substitution again is to convert the complexity into a simplicity. Now look at this. Is this a simple? Now take note that if we say simple, we can use the basic integration. But the question is, do we have the theorem for evaluating secant? Okay. Nothing. Okay. We have no secant here. So the best thing to do again is to continue take another technique. No, one based on experience. If we have secant, we can do it this way, rationalizing. This is just an assumption, okay, that maybe it helps to reduce this one, to change the mood of this, so that we can integrate. Because just when you look at this one, it's just like simple, but this is not a simple for the reason that we have no available integral of secant. So therefore, best thing to do is to, or another option is you have to look in the table. Okay, but the strategy is to rationalize. Multiply this, try this. Secant theta plus tangent theta. This is 1. So meaning there is no changes of the previous expression because this is just 1. Okay, then next is to cross multiply. Okay, or distribute. So therefore, this will become secant squared and this is secant tangent theta. Okay. Now notice, it looks like it returns to another complex, no? But there is a strategy of this. Now look at this one. So if we use the substitution, methods of substitution, integration by substitution, we can let this u, because this is composite, no? We can let this be equal to u. Let this be equal to u. So therefore, that's the result. Now, which means that we will convert again. The theta should be converted in terms of u. If you remember, notice previously, the y was replaced to theta. Now this time, because we did not successful to have the basic using the theta, we will move again to u. So let this be equal to u. So this is secant theta plus tangent theta. Take the derivative of that with respect to theta. Now take note, the derivative of secant is secant theta tangent theta. This is basic differentiation technique or formula. Now take note, the derivative of theta is secant squared theta. And this theta is du over d theta. We cross multiply so that we have the value of, okay, we have the value of d theta. But take note, we need theta. So therefore, divide this both sides by this one so that we can solve for theta. And that d theta will be replaced here. And this one, take note, this is u. Okay? So solving for d theta again, divided by this result. Okay? So du is over secant theta tangent theta plus secant squared theta is our d theta. So everything, this one should be replaced here, and this one should be u. Okay, the u value. So do it. Okay, this is it. Your du, okay, your d theta is again what? Is again du over secant theta tangent theta plus secant squared theta. Now, what is your, this one, denominator, secant theta plus tangent theta? It should be the u value. So therefore, this one is the same. Nothing has changed this one as is. Okay. Then again, this will becomes the u, and d theta, d theta is this one. Okay, so this is the d theta. Now again, look at this one. Why is it we do it this way? Now look at this one. This is exactly the same. Okay, so we can cancel it out. So look at the result. Amazing. We're living with du over u. Okay, so take note. This is now basic because this is. By the way, if you place this to the numerator, this will become negative 1. But the integral of x raised to negative 1 dx or u raised to negative 1 du is a natural logarithm. Okay? So it is an ln of u. Take note that we cannot use the power rule because the exponent, if you place it in the numerator, negative 1. But we have a special formula that the integral of du over u is ln u. And take note the limit is from negative a to a. So we are able to evaluate the integral of the two technique. First is we use the trigonometric substitution. We are not successful. We change the theta y in terms of theta. Then after that, we replace theta in terms of u, and it is the u. Letting you makes the integration simple. This is now basic, can be treated basic because we have the value of the integral of du over u. Okay, now the problem is this negative a and a limits is intended for what? Intended for the y limit, because this is talking about the y should be ranging from negative a to a. So therefore, we need to replace u. Okay, so go back, this is just a dummy variable, the u. So we'll substitute again the u. The u, take note, is secant theta tangent theta. So replace this with secant theta tangent theta. So here's it. Here's it. This is u. U is secant theta. Now I use absolute because the natural logarithm, the number should be a positive answer. So in case of negative, consider only the positive value. Okay. So then, what next? Next is, again, nothing to evaluate the limits because we haven't seen the y, because this is intended for y again. So let's go back again the assignment of y. Now take note that this is our triangle. Okay. We use this as our instrument to convert the y in terms of theta. So we will go back again to y. So how? Now what is secant theta? Now take note, secant theta is the reciprocal of cosine. Now the cosine, remember, is adjacent over hypotenuse. Since secant is the reciprocal, so therefore this must be hypotenuse over adjacent. So secant theta must be what? The square root of x squared plus y squared divided x. While tangent is what? Added by tangent. Tangent is opposite over adjacent. This is the angle. Opposite is y, adjacent is x. So therefore the tangent is simply as y over x. So do it. So this is secant, okay? This is hypotenuse, okay? We have this as the adjacent, so therefore this is secant again, correct? And this one plus added by tangent is y over x, opposite of adjacent. Okay. So we are now on the way to evaluate the limits because we have now seen the presence of y. X, this is given, y is variable. So therefore, take note, upper minus lower. Okay? But, okay, so therefore, do it. Upper, substitute y, everything y with a. So, this is y squared, so will becomes a squared, and the y becomes a plus, okay. Then, lower limit, minus, okay. Natural logarithm is still there. And this is the number logarithm, the square root, okay. As is, instead of y, take note that we will replace negative a, okay. But squaring negative a becomes a positive a. So, the same. This is square root of x squared plus a squared. Okay. Then minus y. and this time negative. So therefore, this should be negative. Okay? So, look at the result. Take note that, okay, we have the common value of x, common denominator. So, this will be simplified as this one. Then minus, okay, common denominator again. So, therefore, we have this one. Now, again, we can compress this one. The two terms involving natural logarithm. Why? Because this is ln and this is ln, meaning this is log base e. This is log base e. And this is minus. Recall again the property of logarithm. If we have the same base and they are subtract forming difference, meaning we have this sign, then according to the property, it should be this one, natural logarithm of this minuend, okay, number, divided by the subtrahend number. So therefore, we can compress this and forming only one natural logarithm by what? Taking the ln, then this is our numerator and this is our denominator, then quantity. This is the result. Okay. So again, this one can be compressed in terms of this. One natural logarithm present. Okay, so again, these are the same. So then, we can cancel the x. Okay, we can cancel the x. So therefore, okay, so this is now our final answer. This is the electric potential of a finite line charge. So therefore, this is only intended for the infinite line, or sorry, finite. This should be replaced, removed. This is not infinite. This is for a finite, which means when we say finite, the length is known. Okay, finite line charge. Okay, so therefore, if you are asked how much is the potential at point P of the finite because given this the length of the line is 2a. So what is the potential at P at with distance x? The answer is no need to know this r, no need for r, because we need only what? The charge of that conductor. We need the A. Take note what is A. This 2A is L. Okay, or the length. So which means that if you are given length here and you want to solve what is A, you just divide it by 2. Okay? For example, the length of the wire is 15. So what is A? 15 divided 2 and it is 7.5. So therefore, 2 times 7.5. So we need A because this one is, take note, is the 1/2 of the length. So therefore, if x is given, you want to know how much is the potential at that point, then substitute it. Then this is the result. Now, if this charge is positive, then your potential is positive. Okay? So, I think we answered the question, what is the potential of a finite line charge? Thank you for listening. See you in the next video.